This is a tutorial describing how Lewis structures are formed. It's an important topic because the ability to draw Lewis structures is going to help us tremendously in understanding the three-dimensional structures of compounds. But this is a topic that we need to master first. We're going to start by talking about how ionic compounds are formed. Ionic compounds are formed from one element on the left-hand side of the periodic table, where we find our metals, one element from the right-hand side of the periodic table where we find our nonmetals. Typically, what we've got then is we have a metal with a low first ionization energy, a nonmetal with a high electron affinity, and during the course of the reaction, an electron from the low ionization metal completely transfers an electron to our high affinity element. Our now positively charged cation has a smaller radius. Our negatively charged anion has a larger radius. And then these cations and anions are stacked into a crystalline structure that looks something like this. Our positive and negative ions are held together in a solid material by something that's referred to as the lattice energy. And we can calculate the lattice energy using Coulomb's law once again, which describes the force or energy holding together charges that are dissimilar. For molecular compounds, we're going to draw Lewis structures. These molecular compounds are held together by covalent bonds rather than ionic bonds. We have a set of rules for Lewis structure that looks something like this. The first thing is we're going to ignore all of the core electrons as we're drawing Lewis structures. Core electrons are the electrons that are in the completed principal quantum number of n. So basically everything outside of the valence electrons we're going to ignore. We're then going to ask ourselves how many valence electrons there are for each atom, and we're going to have to account for those valence electrons in the molecular total number of electrons when we're done forming our Lewis structure. Hydrogen atoms are always terminal. We find them at the end of the molecule. Hydrogen atoms can only accept one electron to complete their principal quantum number of n equals 1, which means that hydrogen atoms can only form a single bond. We will never find them inside of a molecule. Halogens are almost always terminal, almost always forming a single bond. If we find a halogen in the middle of a molecule, and we'll see some examples of that, it means that we've expanded beyond our octet. The more electronegative atoms tend to be terminal, not found in the middle of molecules, but tend to, or almost always indicates that sometimes we find that that's not the case. When we form our bonds, we're going to try to complete octets, having filled out both the s and p orbitals, or a duet in the case of hydrogen. We will account for things like non-bonding electron pairs. We'll see examples of that as we go through and form our Lewis structures. We may be forced to form double or triple bonds when necessary, which means that we will share more than 2 electrons. In the case of double bonds, we'll share 4 electrons. Triple bonds will share 6 electrons. Starting with the n equals 3 principal quantum shell, or the third row in the periodic table, we may also be forced to use d orbitals. We should also consider molecular charge, which means either we've got additional electrons above and beyond the valence electrons, or fewer electrons than predicted by our valence electrons, which will force us to add or subtract electrons based on the charge. So for instance, a carbonate anion, CO3 2 minus, has extra electrons. And you should be prepared to either add or subtract electrons from our valence structure based on those charges. Again, we'll see examples of that. All right, so let's talk about how we're going to form our Lewis dot structures. The first thing that we need to remind ourselves is we need to follow the valence electrons, and as the name suggests, we'll use a dot to represent each of the valence electrons. So lithium, for instance, which is group 1, has 1 valence electron, and we would draw lithium with a single dot. Beryllium, which is group 2, will show 2 dots, and in this case, the representation we've shown indicates that those dots are paired in the 2s orbital. Boron has 3 valence electrons. We would typically show it with 2 electrons paired, 1 electron unpaired in the p orbital. Carbon, nitrogen, oxygen, fluorine, and neon, as we go through the group 2 elements, would be shown like this. Well, the objective in drawing Lewis structure is to complete either a duet, I'm sorry, an octet, or a duet in the case of hydrogen, by completing our p and s orbitals. So if we draw the Lewis structure for 2 nitrogen atoms shown like this, we see that we have 2 electrons paired in the s orbital. We have 3 unpaired electrons in the p orbitals. The only way that we can share electrons and complete an octet for both of these nitrogen atoms is by pairing up all of the electrons that are independent in those p orbitals in a symbology shown like this. So now if we analyze the electronic structure for each of those nitrogen atoms individually, we find that they now have an electronic structure of 2s2, 2p6, 2 plus 6 is 8. We have filled out the octet for each of the individual nitrogen atoms by sharing 3 electrons each. We can further go ahead and simplify the structure by showing lines connecting those atoms, where each line represents 2 electrons. So in this representation, we have a nitrogen molecule N2 where we are sharing 6 electrons, and then each of the nitrogen atoms has 2 electrons in a non-bonding electron pair. Well, let's take a look at the next example in row 2 of the periodic table, oxygen. Each of our oxygen atoms has an electronic structure of 2s2, 2p4. Each of those oxygen atoms is short 2 electrons of completing an octet. If they share their unbonded p electrons, they both are capable of reaching an electronic structure of 2s2, 2p6, 2 plus 6 equals 8. We have finished out our octet. And again, we would show an oxygen molecule in a Lewis dot structure showing 2 lines connecting them, each line standing for 2 electrons being shared in a bond. And now each of the oxygen atoms has 2 non-bonding electron pairs. If we count up the number of electrons around each oxygen atom, we see we have 8. Finally, let's finish off with group 7 in the second period of the periodic table. Each of our fluorine atoms has an electronic structure of 2s2, 2p5, 1 electron away from an octet. Each of these fluorine atoms then will share their single unpaired p electron, achieving a 2s2, 2p6 electronic configuration, and we would then show these paired electrons with a single line indicating a single bond, and now each of those fluorines has reached an octet. We have to understand that what we've just shown is bookkeeping, not reality. All right, it's a way of keeping track of our valence electrons and how our valence electrons are paired up in single, double, or triple bonds. But this is not reality. We need to remember that as we move on to our molecular structures, which are meant to reflect reality. So again, looking at these, how many electrons are being shared in an N2 molecule? Well, if we look at our symbology, where we have 3 lines, a triple bond holding those 2 nitrogen atoms together, each of the lines representing 2 electrons, we have 6 electrons being shared. In oxygen, we have 4 electrons. In fluorine, we have 2 electrons. Once we reach the third period, or row 3 in the periodic table, we have access to d orbitals, and the situation becomes more complex. We'll address that in a couple of slides. Well, let's look at covalent bonds and Lewis dot structures for things other than simple diatomic molecules. What happens when we have two high electron affinity nonmetals? So we have elements from the right-hand side of the periodic table. If we have two elements from the left-hand side, we get metallic bonds. If we have one element from the left-hand side, one element from the right-hand side, we get ionic bonds. When we have two elements from the right-hand side of the periodic table, both with high electron affinities, they want to gain electrons, we end up with covalent bonds as these elements share electrons. Well, let's take a look at at putting together a simple molecule like water, both hydrogen and oxygen on the right-hand side of the periodic table. Although you'll notice in most representations of the periodic table, hydrogen appears both as a group 1 element having one valence electron and a group 7 element missing one electron to complete its shell. Well, in this case, we're treating hydrogen like a high affinity nonmetal. So we start out with 1s electron. Oxygen starts out with 2s2, 2p4, missing 2 electrons. And we're going to end up with each of the hydrogens sharing one of the unpaired electrons from oxygen, completing its duet. Oxygen sharing one electron from each of the hydrogens, completing its octet. In this way, hydrogen has completed a 1s2 configuration. Oxygen has completed a 2s2, 2p6 configuration, completing its octet. You can see that for oxygen in this molecule, we have two non-bonding electron pairs. By sharing electrons in covalent bonds, all of the atoms have achieved a noble gas configuration filled shell. The hydrogens have completed a noble gas configuration of helium. The oxygen has completed a noble gas configuration of neon. Well, let's consider another simple molecule, carbon monoxide. We would show our valence electrons starting out for our Lewis structures looking like this. And you can see that oxygen would share 2 electrons to complete its octet. But in this situation, if we take a look at the number of electrons around each individual atom, we have 8 electrons around oxygen having completed its octet. But if we take a look at carbon in this symbology has 2 electrons in a non-bonding electron pair. It's sharing 4 electrons with the oxygen, and that gives us 6. We have non-bonding electron pairs in both the carbon and the oxygen. Has carbon completed an octet? No, it has not. It is showing a configuration of 2s2, 2p4. It is 6 electrons. It is 2 electrons short of completing its octet. And as a result of that, carbon monoxide is a very reactive compound. Biologically, it will latch on to hemoglobin, blocking hemoglobin from its job in shuttling oxygen molecules back and forth between tissue and lungs, and ultimately killing biological organisms. So carbon monoxide will do almost anything to grab the 2 missing electrons. Let's take a look at another simple molecule, ammonia, NH3. Well, you can see in the Lewis structure configuration we've shown here, nitrogen is short 3 valence electrons from an octet. By sharing 1 electron each with hydrogens, it completes its octet. And of course, we can see that the nitrogen has 1 non-bonding electron pair, a pair of electrons not involved in bonding. But we can form a simple molecule called ammonium, NH4 with a plus charge, by reacting ammonia with a hydrogen ion in solution. In this case, we now have 4 hydrogen atoms clustered around the nitrogen. And that hydrogen with a plus charge has no electrons. it ends up sharing both of the non-bonding electrons from the nitrogen, and we end up with a plus charge on the overall molecule. So if we had a hydrogen atom with one electron and try to add it to ammonia, we would have 9 valence electrons, 1 over a noble gas configuration, no reaction. But if we try to react with a hydrogen ion, which is not bringing any valence electrons to this reaction, we still have an octet around the nitrogen. We have reached a noble gas configuration. And each of the individual 4 hydrogens also has reached a noble gas configuration. Overall, we have a plus charge on the molecule. Well, let's take a look at carbon dioxide, a relatively simple molecule. We're going to bring in our carbon, and now you can see that I have separated my individual valence electrons in carbon into 4 separate areas so I can use them all for bonding. I'm going to end up sharing unpaired electrons with the oxygens, 2 each for the oxygens. And if I go ahead and draw my Lewis structure for that molecule, I see that I have a double bond. I've shared not 2 electrons, but 4 electrons between the individual carbon and oxygen atoms. And if we count up our valence electrons around the oxygen, we can see 4 electrons around from the non-bonding pairs. We're sharing not 2, but 4 electrons with the carbon. Each of the oxygens has reached an octet. If we do the same analysis around carbon, I see 4 bonds, each of those bonds representing 2 electrons for a grand total of 8 electrons around the carbon, and I have filled out my octet. So each of the atoms in this molecule has reached a noble gas configuration, a very stable molecule. Well, let's add 1 extra electron one extra oxygen into this situation for a molecule called carbonate, which actually carries a -2 charge on it. That indicating that we've got 2 more electrons in this molecule than would be indicated based on valence electrons. So let's go ahead and draw out our valence electrons again for each of the individual oxygens and for the carbon, and see what kind of bonds we're likely to form. Well, the first thing that we're going to do is we're going to share 1 unpaired electron between each of the oxygens and our central carbon. Once we do that, we see that each of the individual oxygens has reached 7 electrons, not 8. The carbon has also reached 7 electrons. And by sharing that last unpaired electron with carbon, we end up with a situation where we're double bonded to one of the oxygens, single bonded to each of the other oxygens. The double bonded oxygen has reached an octet. My carbon has also reached an octet if we look at the individual bonds. But the other 2 oxygens are at 7 electrons. They have not reached an octet. Well, this is where our 2 extra electrons come in, the -2 charge on the molecule. Those 2 extra electrons have been picked up from somewhere in the environment. We don't necessarily know where. And as we insert each of those electrons into the other 2 oxygens, now all of the oxygens have reached an octet, and we have a stable molecule. Well, we have exceptions to the octet rule, and let's see where those exceptions show up. Sometimes we have incomplete octets, meaning we have not reached 8 electrons. Let's see where we will find that and why. Uh, we'll start by looking at a molecule like aluminum chloride. If we take a look at aluminum in the periodic table, we'll see aluminum is group 3, which means it has 3 valence electrons. If we take our individual chlorides, which have 7 valence electrons, 1 short of an octet, we can share one of the aluminum valence electrons with each of the 3 chlorines indicated in the molecular formula. Well, if we analyze this structure, we see that each of the chlorines has reached an octet. But aluminum only has 2, 4, 6 electrons around it. Has not reached an octet, but it has no more valence electrons to share in additional bonds. So aluminum trichloride, shown here in its Lewis structure, is an example of an incomplete octet. And of course, we've already looked at carbon monoxide, which we would show in this type of Lewis structure configuration, where we've got 2, 4, 6, 8 electrons around the oxygen, but only 2, 4, 6 electrons around the carbon. Sometimes you'll also see carbon monoxide shown this way, where we are sharing not a double bond, but a triple bond with the oxygen. And now, if we count the electrons around the carbon 2468, the electrons around the oxygen 2468, they have both completed an octet. But one of the pairs of electrons being shared came completely from the oxygen, because oxygen is not sharing one electron, but sharing both electrons. We have a formal positive charge on the oxygen. The carbon has not contributed an electron in that last shared pair. We have a formal negative charge on that carbon. Since oxygen is more electronegative than carbon based on our understanding of electronegativity, and would not be interested in sharing that extra electron pair, this is an unlikely Lewis structure where we've got a positive charge on the more electronegative atom, a negative charge on the less electronegative atom. Although it is a valid Lewis structure, this is not something we would normally see in terms of reality in the laboratory. Sometimes we will also have odd numbers of electrons, which result in unpaired electrons in our molecular orbitals. We refer to molecules that have unpaired electrons as free radicals, and not surprisingly, these molecules are very reactive in the laboratory and in biological systems, as these molecules try to grab an extra electron to finish out that octet. An example that's important in biological systems is nitric oxide, NO. If we go ahead and draw our Lewis structures, we get something that looks like this. We can see that oxygen has filled out its octet, but the nitrogen has an unpaired electron. And nitric oxide in biological systems is an important molecule for regulating things like blood pressure, and other pharmaceuticals are based on the generation of nitric oxide. Hydroxyl radical, so we're used to seeing hydroxide, OH minus. A hydroxyl radical forms we've got an oxygen forming a single bond to hydrogen. This oxygen now has an unpaired electron, which makes it very unstable and very reactive. In biological systems, errors in metabolism will generate hydroxide radicals. And current research thought is the generation of these hydroxide radicals inside of our cells is involved in both the aging process and in the generation of mutations. These compounds will be attracted to anything where they can grab that extra electron to fill out their octets. Finally, we should look at compounds that use d orbitals in these types of Lewis structures and end up expanding beyond octets. So bonds to very electronegative elements can force other elements in those molecules to expand beyond an octet into d orbitals. So where are we going to find elements that have very high electronegativities? So typically we're looking at molecules that contain fluorine or oxygen. At least in general chemistry, we'll limit ourselves to those. And then we also have to consider where in the periodic table will we find elements that have d orbitals. Well, the periodic table starts showing d orbitals in row 3, period 3. If we're looking at elements in period 2, we do not have access to d orbitals. So let's take a look at a few examples of where we're going to expand beyond an octet using d orbitals. We'll first look at a very simple molecule called triiodide. Iodide meaning we have a negative charge. Triiodide is an anion, meaning that we'll have to account for an extra electron. Well, let's start out with one iodine. Iodine is in group 7, the halogens, 1 electron short of an octet. And if we bond 2 iodine atoms together in an I2 molecule, which is a perfectly reasonable representation, I2 exists. It is the natural form found for iodine. We've got both of these iodine atoms having completed their octet. But if we can force this stable iodine molecule to bond to another iodine atom, we've got again 7 valence electrons. Both of the iodines in I2 have completed their octets. The only way we can form an additional bond is by taking one of our non-bonding electrons and promoting it into an empty d orbital. Now the remaining electron in that p orbital is unpaired. We can pair that up with the additional iodine atom that we're bringing in. So now we've got an octet in that third iodine atom we've brought in. That unpaired electron in the d orbital is unstable. Those electrons like to be paired. Well, luckily we have an extra electron in this molecule that we picked up somewhere from the environment, we don't know where, and now we have paired electrons in that d orbital in an overall negative charge. When we write our Lewis structure, we would show something like this, and I've designated that extra environmental electron as red. And overall, we would show the charge on this molecule as a -1. We wouldn't necessarily show it on the central iodine, even though that's where I have the electron located. So we would ask ourselves the question then, how many electrons around the 2 terminal iodines? Well, if we count that up, we see 3 pairs of non-bonding electrons, that's 6, plus a shared pair of electrons, that's 8. How many electrons around the central iodine? Well, if I look at that, I see 2, 4, 6 electrons in non-bonding electron pairs. And then I see 4 electrons in shared electron pairs for a grand total of 10. We have expanded beyond the octet rule that we've been practicing up until now by using our empty d orbitals. Okay, let's move on to another example. Let's take a look at sulfur dioxide, SO2. Well, both sulfur and our oxygen start out with 6 valence electrons. We're going to start out by sharing unpaired electrons in the sulfur with each of the oxygens. And when we do that, sulfur has completed its octet, but the oxygens have not. Oxygens are more electronegative than sulfur based on their positions in the periodic table. And they will force one of the electrons, one of the paired electrons in sulfur out of a p orbital into a d orbital. And now we've got an electron left unpaired in that p orbital. We can share that with one of the oxygens. We have an unpaired electron in that d orbital. We can share that with the other oxygen. And we have then a Lewis structure that looks like this. If we take a look at the electrons around each oxygen, we see 2 pairs of unpaired electrons. That's 4 electrons. We have double bonds. That's another 4 electrons. Each of the oxygens has achieved an octet. Sulfur, on the other hand, has 2 non-bonding electrons and then a double bond with each of the oxygens. That's 4 electrons involved in bonding. That's 8 electrons plus the 2 electrons as non-bonding, as a non-bonding electron pair. Sulfur now has 10 electrons. It has violated its octet because it is bonded to a very electronegative atom, oxygen, and it has access to those d orbitals. Let's take a look at one more sulfur example, which is sulfate, an anion with a -2 charge. Again, we're going to start out with our sulfur. We're going to share non-bonding electron pairs. to complete the octet around sulfur. Both of those oxygens are not completely bonded, not completely at the octet. But we'll notice that our molecule is an anion. I have two extra electrons from the environment somewhere. Well, if I assign both of those electrons to the oxygens, one each, sulfur has completed its octet. The two oxygens have completed their octet. But the molecule shows four oxygens. I still have two more oxygens that I need to account for. Each of those oxygens is two electrons short of an octet. If I go ahead and take those non-bonding electron pairs on sulfur, I promote one of the electrons into a d orbital. Now I have an unpaired electron in the p orbital, an unpaired electron in the d orbital. And my oxygen can form bonding pairs with both of those unpaired electrons. That oxygen now has achieved an octet. Again, on my other non-bonding electron pair, I'm going to promote one of those electrons into a d orbital. I now have two unpaired electrons on sulfur. I'll go ahead and share those two unpaired electrons with the two unpaired electrons in oxygen. And now both oxygens have completed their octet. Well, let's go ahead and show our bonding electron pairs with lines rather than dots, so that we can keep track of these. The symbology we would use then shows two of the oxygens double bonded to sulfurs, both of those oxygens having completed their octet. Two oxygens single bonded with sulfurs, but having taken two electrons from someplace in the environment to complete their octets. And overall, the molecule has a -2 charge. If we take a look at the individual oxygens, we see they have both completed their octets. Sulfur, on the other hand, has 2, 4, 6, 8, 10, 12 electrons around it. Sulfur has expanded well beyond its octets by using d orbitals to bond with the oxygens that are more electronegative.